In this part of this probability course, we will look at the introduction to probability, random experiment, determination of measure probability, some basic laws of probability of compound and event. But with this video, we are going to look at review of set theory, which falls under the introduction of probability. Probability theory uses the language of sets. In this video, I'm going to brief you on some concepts from set theory that are used in probability. We will also discuss some set notations, definitions, and operations, such as the union and the intersection, and more. When we talk about set, a set is a collection of some items, which can be elements. We often use capital letters to denote a set. To define a set, we can simply list all elements in a curly bracket. For example, to define set A, that consists of two elements, which is this, that. We write that set A, which is A, is this. To say that this triangle belongs to set A, then we write where this notation is pronounced belongs to. To say that an element does not belong to a set, we use, for example, we may write which means circle does not belong to set A. Let's note something here. The ordering does not matter. So the two sets are equal. We often work with set of numbers. So let's look at some important sets that are given in the following example below. The following sets are used in probability. Now, the first set you're going to look at is the set of natural numbers, and it is represented by n. 1, 2, 3. The set of integers, which is z. The set of rational numbers, which is q. The set of raw numbers, which is r. We also have closed intervals on the raw number. For example, we have 2 and 3. This is a closed interval. is the set of all real numbers x such that x is greater than or equal to 2, less than or equal to 3. And for an open interval on a row line, for example, is the set of all real numbers of x such that -1 is less than x and x is also less than 3. Similarly, we could have a combination of a closed set and an open set. So in this case, we could have an example 1 and 2. And this is a set of all real numbers x such that x is less than or equal to 1 and less than 2. We could also move to set of complex numbers. C is a set of numbers in a form of a plus bi, where a and b belongs to real numbers and I is equal to root of -1. We can also define a set by mathematically stating the properties satisfied by the element in the set. In a particular, we may write that A is equal to or. So in this case, the symbol this and that are pronounced such that. So in this case, when we are reading this, for all s is such that S satisfies some property. The same thing applies to this. X is such that S satisfies some property. Let's look at example 2. Here are some examples of sets defined by stating the property by the element. So the first one we're going to talk about is if the set C is defined as C is equal to then C will be so how do you read this? C is equal to X is such that X belongs to Z, in which Z represents the integers. So X is greater than or equal to -2 less than 10. So we could write this as S is closed at -2 but open at 10. We could also write in this way that the set of rational numbers can be defined as what? A Q. In this case, it's equal to A over B, such that A and B are what? Belongs to, or A and B belongs to integers, that is Z, but B should not be equal to 0. These are all properties that one must know. We could also have for real numbers. So for real numbers A and B, where A is greater than less than B, we can write that AB is equal to X belongs to real numbers such that A is less than X, less than or equal to B. Very nice. Now let's move on to some continuation of the definitions of set. Set A is a subset of set B if every element of A is also an element of B. We write that A is a subset of B if every element of A is also an element of B, where this sign or this notation indicates subsets. Equivalently, we say B is a superset of A, or B is a superset of A. Let's look at some example. If E, example, if E is equal to 1 and 4, and C is equal to 1, 4, and 9, then we can say that E is a subset of C. And from here, we can generate some identities that N is also a subset of Z, and also Q is also a subset of R. Natural numbers are subsets of integers, and rational numbers are also subsets of what? Real numbers. Now let's move on. Two sets are equal if they have exact same element. So A is equal to B if and only if A being a subset of B and B being a subset of A, then the condition holds. So we could have that a set which is 1, 2, 3 would be equal to 3, 1, 2. But if the set has no element, we could represent it as this or an empty set. And this is called an empty set or a null set. The universal set is the set of all things. So we are looking at the universal set. The universal set is the set of all things that could possibly consider in a context we are studying. Every set A is a subset of the universal set. So every set A is a subset of the universal set. And in this course, we often denote the universal set by the letter S. The universal set is called the sample space in probability theory. Sample space. So in this case, let's look at some example. For example, if you are discussing a rolling die, so a rolling die, we are discussing rolling of a die, our universal set may be defined as S be equal to 1, 2, 3, 4, 5, 6. Or if we are discussing tossing a coin, our universal set might be S is equal to, would get a head or a tail, which is H representing for heads and T representing tails.